Can you see the screen?
Yes, sir.
All right. We will see today an application of this theorem. So, for example, fx is sine x. Right. So this is well known that f prime x is cos x. Right. But what is the proof? Yeah. Can you give a proof?
So we can use first principle definition of derivative.
Of course, you can use this one. So sine of x plus h, whatever, minus sine x by h, and limit h tends to 0. Then
So maybe using sin c minus sin d for the numerator and then somehow bringing it to one sine of some function of x, some function of h, and then using sin x by x, limit of sin x by x goes to 0.
limit of sine x by x goes to.
We can use this property after we use sin c minus sin d on the numerator to put it in sine function, and then
Okay.
somehow use sin h by h will go to 0 on the limit of 0. So sorry, sin h by h will go to 1 on the limit of 0. So
So that is the main, right? So that is the important point. So h tends to 0, sine h by h is equal to 1, right? But what is the proof of this? So what is the proof of this?
series of sin x.
Yes, series
Using the
scalar
series of sin
expansion of
x.
sin x. Yes.
Good. So you ultimately here you get this one by power series expansion. So by the definition of sin x, that is the definition of sin x. So power series expansion of sin x, right? Uh, okay. So what you mean? What we see here that if you have a power series expansion here, then perhaps you will be able to find the derivative in some way, right? So in this case, you write power series of sin x, the definition of sin x by h, and then calculate term by term. Then you interchange the sum and limit, right? So you need to interchange. So here and then an interchange of limit and summation takes place, right? Right. So you have summation here, sum of some a series, and then limit h tends to 0, But what you are actually doing, you are taking sum out and then taking limit term by term, right? In some sense, or yeah, maybe here h comes common as, yeah, right. So in any case, this interchange takes place. Now the question is here, as an application, we will show. Uh, so suppose summation an x minus a power n be a n from 0 to infinity is a convergent power series. Is a convergent power series on a minus r to a plus r. Right, so since this is convergent, convergent means converges absolutely, right? And we know once it converges here, at a point, there will be, by Abel's lemma, there will be an interval where it converges uniformly also. So do you know that? Suppose it converges, A is this point, A is this point, and let's say A plus R is this here, A minus R is this one. Now suppose you uh, take a point C here, right? And assume the series converges at x equal to c. Then the series converges here absolutely. Then the series will converge uniformly on any closed interval on, one can choose this at x equal to a plus c, that would be better. A plus c, so on. Closed interval alpha beta lies in a minus c, a plus c. Is it discussed?
No, sir. I don't think so.
But it's very simple because of the following reason. But yeah, do you see this? Once it converges at one point, so you go this much distance here and same distance this side, and it will converge uniformly on any closed interval inside this, right? It looks little bit stronger, is it? So you see what it converts. So this one. Uh, so proof of this one. This call this as a fact. Actually, this is a real version of Abel's lemma. So this is actually called Abel's lemma. Yeah, this Abel is Abel's variable. So the proof here is very simple. Actually, by comparison test, so you look at model of a n x minus a power n, this one. This is less or equal to, which is of course, this is fine, which is less or equal to mod a n, and this is equal to nothing but mod a n mod x minus a power n. This is c minus a power n for all x in alpha beta, right? So a minus c less than alpha less than beta less than a plus c. Is this clear? Is this inequality clear? See this x minus a. X minus a, what is x minus a here? This is it is increasing and it will attain maximum at c, right? That's what it is. At c it will be bigger. Alpha beta will be somewhere here. It might contain a or not, that doesn't matter. So is this clear?
Sir,
Yes.
sir, in the diagram, the C should be replaced with A plus C, right?
Right. C should be replaced by a plus c. Right, we replaced here by, yeah, thanks. This is a plus c. Right. Right, and so this will be this part. This will be a minus c. Okay, now is this clear? This is this comparison. So what is more important here is this comparison. Clear? X minus a is, right, since x minus a is less than equal to c minus a, right? Because of this.
So shouldn't it be just C and not C minus A?
Yes. I have chosen a plus c, right? That is good. That is a good point. Yeah. So this should be just c. Right. Right, so choosing this one would can create confusion. C power n. So this should be mod C, right? Now is it fine? Hmm? Now see, this is real number. So this should be sum of mod n mod x minus a power n from 0 to infinity will be less or equal to sum of mod n mod c power n from 0 to infinity, and this is less than infinity, right? Because this series converges. Since the series summation n x minus a power n from 0 to infinity converges absolutely at x equal to a plus c, right? So this series, this is less than infinity, and this series will be dominated by this one. So this series converges. So here, well, this part is, so this converges, and this series is less than this one. This is actually kind of a proof of comparison test, but yeah. So therefore, the series in from 0 to infinity, and this is true for, this is for all x in alpha beta in x minus a power n converges absolutely and uniformly on alpha beta. Is this clear? So this kind of series, if it converges at one point, means it has actually an interval of convergence. Is this clear? Any question here?
So this may not work if it doesn't converge absolutely at the point C, right?
Right, right. But what is important is at one point it converges, means you have one point except the point A, right? At point A, this series is 0.
So it should converge absolutely at one point. Not the
Yes, absolutely at one point except the point A. Then you get an interval on which every closed interval inside that you have a uniform convergence, right? So proof is simple, but this is very important. I mean, those who will do complex analysis later on, you will see this is just generalized to complex variable. And this is there in my complex analysis videos also. Now our question was, we want to take derivative of this series. So this series gives you a function. So if summation a n x minus a or n from 0 to infinity converges absolutely on a minus r to a plus r, then we can define a function g from that interval a minus r to a plus r to real line by gx is equal to n x minus a power n from 0 to infinity. Okay? All right? So once it is converges, it will give at every point of this one a real value. Hence, it will define a function. The real value will be unique. Hence, it will define a function. Now, question is, first question, is G continuous?
Yes, sir. I mean,
Why?
because each of those functions will be continuous and it converges
And
uniformly because we assumed it converges absolutely.
it converges absolutely on every compact. It
Uh,
might not converge uniformly on this open interval.
okay, so then G will be continuous on the closed interval A minus R A plus.
No. See, continuity is a local property which
Oh, no,
always shows
at all the
continuity at
points on
A.
the, yeah, it will be continuous on all the points in the closed interval.
No, it will be continuous on any on this whole thing. So to check continuous, you fix a point, right? Fix
Yes,
a, and that will be contained inside and closed interval.
yes.
So it will converge uniformly there.
Yeah,
Right? See, you see this continuity comes from uniform convergence, but what you need uniform convergence on compact, not uniform convergence on this open interval. So G is continuous. So is the argument clear? Because the series converges uniformly on every closed interval alpha beta such that a minus r less than alpha less than beta less than a plus r. Right, so is the argument clear? This converges uniformly on every closed interval. Now, if you want to continuous, you want to show continuity at a point, right?
yes, sir.
At a point, at every point. So fix a point. Let's say x naught. So you'll get a closed interval containing x naught inside this. So the series will converge on that closed interval uniformly. Hence, it will be continuous at that point also, right? Yeah, is it clear to everybody? Then I'll go to the next question.
Sir,
Yes?
it is also differentiable, right? From the last theorem,
Yeah, so that is the
using
next question. Is G differentiable? Why?
because it is already like convergent on the range, and it is uniformly convergent on every closed subset, right?
Every compact subset or
Yes,
closed
yes.
interval, closed subinterval. Yeah, so does it uniformly convergent sequence of differential function gives you differentiability? So last theorem had certain conditions also, right? Yeah. What are the conditions of the last theorem we had? We proved. Hmm.
F, F dash and had to converge uniformly.
Hmm. So F dash also has to converge uniformly. Does this happen here? So you need to get the sequence. So what is the sequence actually? Hmm?
It will be like a1 x minus a2 x minus a squared, and so on.
No, that is not a sequence. The sequence will be the sequence of partial sums.
Okay, okay.
So for a series, the corresponding sequence you want to look at and it converges uniformly and you want to apply a theorem for sequence of functions, then the member of the sequence will be sequence of partial sums. All right. So what is the sequence of partial sums in this case? So answer is yes. It is differentiable and right. So here and and G prime X will be summation n from 1 to infinity n x minus a power n minus 1. The term-wise differentiation, you see? So derivative, so it is interesting question. No? You can differentiate each term. You can differentiate each term and look at the summation, whether this gives you the derivative. In this case, it does. It gives you the derivative. And this is true for all a minus r to a plus r. For all x in a minus r to a plus r. And whoever was saying that by previous theorem, uh, that was the correct argument. That was the correct argument. So let me give you a proof of it. Proof of the above. So, or the justification of this answer. Justification to the answer. Okay. So you consider the following sequence. You have to consider the sequence fk. Consider this. Consider fkx summation an x minus a power n from 0 to k. All right. Is this fine? So, what you, so fk is this one. Clearly, fk is a polynomial, and hence differentiable, right? And we know fk fk converges to f uniformly on every closed interval alpha beta inside a minus r to a plus r. All right. Yep. So fix a closed interval alpha beta. We will show that it converges, the derivative also converges uniformly on alpha beta. Now what is fk prime? Right. So fk is differentiable. We already know. So fk prime will be summation n from what? 1 to k n an x minus a power n minus 1. Right? Is this fine? Fk prime is this one.
Yes, sir.
Right. Now question is the whether Fk prime converges uniformly or not. In turn, question is whether this power series converges absolutely or not. Right? So we need to show by in view of Abel's lemma, we need to show that the series summation n equal to 1 to infinity n an x minus a power n minus 1 converges absolutely on a minus r to a plus r. Does this converges? Suppose the radius of convergence of this one an x minus a power n from 0 to infinity is r1 and the radius of convergence of the derivative one x minus a power n is r2. Now what is the formula? 1 over r1 is equal to lim sub n tends to infinity mod an whole to the power 1 over n, right? Yes? These are the radius convergence is related, right? You get radius of convergence. And 1 over r2 is lim sub n tends to infinity n power 1 over n, which is lim sub n tends to infinity n power 1 over n mod n power 1 over n, right? Yes?
Yes, sir.
And check this is equal to limit, since limit of this exists, n to the power 1 over n times limit mod n to the power 1 over n. So check this part. And what is limit n to the power 1 over n?
1.
Yes. So this is 1. So this is 1 over r1. So this implies the radius of convergence of, and this implies r1 equal to r2 summation n from 0 to infinity n x minus a power n is the radius of convergence of summation n from 0 to infinity n x minus a power n minus 1. Right? So this implies fk prime converges. This implies the sequence fk prime converges uniformly on every closed interval let's say here we put gamma delta. Since alpha beta, we fixed alpha beta, a minus r to a plus r. We get uniform convergence here. We get by using Abel's lemma. So this implies f is differentiable and by previous theorem. Any question?
Sure.
Yes? Yes, yes.
Oh, no, sorry. I didn't realize I was unmuted.
So f prime x is n x minus a power n minus 1 and from 1 to infinity. Right, so is this clear? So the power series, wherever it converges, it converges absolutely uniformly on compact subsets, and the derivativity is also term-wise difference. The series considering the term-wise derivative also converges, and that is actually the derivative of the function given by the power series. All right. Now this is a corollary. A power series is infinitely differentiable on its interval of convergence. Or the domain of convergence, whatever you say it. Domain of convergence. Is this clear? So this is once differentiable. Now you repeat the procedure again with this path series. So it is second derivative also exists. And continue. So all the derivative exist. Yeah? Is it clear? Yes? So a path series wherever it converges, it gives an infinitely differentiable function. All the derivative exists. But of course, this is the converse of this is not true. We will show that there exists an infinitely differentiable function which cannot be given as a path series expansion. Remark, the converse is not true. We will give an example of an infinitely differentiable function function which cannot be expanded as path series. All right? Is this clear? Any question? All right, so look at the notes. I'll send the notes. I have uploaded yesterday's video. I didn't send the note yet. And look at this one. This is very important. A path series is infinitely differentiable, but we'll see next time what the converse is not true. You can explicitly construct an example. That is even more interesting. Okay, so we'll see you on Friday.
Sir,
Yes, yes.
if we just go through Taylor expansions, we basically take f dash x into x minus a plus f double dash x minus a whole square, something like this, right? So if all of f dash, f double dash, f triple dash, all the derivatives are exist, then f(x) should have a power series expansion, right?
No,
Because all
that
of
is
these
not
exist.
always true. We'll give an example where all the derivative exist, but you can't have power series expansion. Of course, you can have Taylor series expansion with remainder. We'll come to that. Taylor series part we have not taught yet. That is also in the syllabus. So yeah, that is what my point is. You have Taylor series, finite Taylor series expansion, but you will not get power series expansion. So just given by if the function is given to be differentiable of all order, even then power series may not exist. So we'll construct an example and showing that the derivative at a point is zero for all points, for all the derivatives to be zero. So the power series, if it is given, then it has to be zero. Okay.
Sir, do you have an example which is like nowhere
power series, like at no point uh,
Yeah.
power series, or do you mean at a single point there will not be a power series
We'll
around a
provide a
single?
single point. We'll provide a single point. 1 over x is not differentiable at x equal to 0. So first you give a single point at one point only. Then you can construct with more points. But this is important to construct a single point. So there are example of continuous functions which is nowhere differentiable. Those things are there. We'll give example of those things as well. But yeah, this is a bit quite interesting. So once you have power series, you can do say a lot of things. You can say in terms of coefficients what the derivatives at that point are, how it behaves. But when there is no power series, then the methods are different. There are Taylor series expansion which will come, but then Taylor series is local. It is in a small neighborhood of that point. This is valid. It's not valid everywhere. Here there is a radius of convergence, but there in a, I mean, small neighborhood it valid. Any other question?
Sir, somebody said 1 by x in the chat. If we define 1 by x on the interval open 0 comma infinity,
Yes.
then we may not have a power series. In this
No,
interval,
no.
what
It will have power series.
everywhere differentiable.
It will have
Okay,
a power series at all the points
okay,
except the zero,
okay.
except the point zero. You can try to construct that. That is very interesting. It's using geometric series, nothing else. But 1 over x is not differentiable at 0, so you cannot consider it 0. So any rational function px by qx always have power series except the points where q is 0. Well, we'll come to, I
So
mean, you
can
will
you give some
see
hint on the construction of this function? I mean, I'm very interested in it. Maybe I'll try. Can you give some
what?
hints? Can you give some hints on how to construct this function?
Using exponential. You try with e to the power minus 1 over x. Minus 1 over, yeah, minus 1 over x.
Okay, sir. Okay, sir.
At x not equal to 0 and 0 at no, actually it's 0 in the negative axis and 0 as well, and at other point it is to the minus 1 over x. Okay,
Okay, sir. Okay, sir.
so try with that one. Yeah, any other question? All right, then we'll see you on Friday.